Welcome to chapter 13.4. Now this chapter is about Green's theorem, and before we go to the Green's theorem, I would like to give you some definitions. The first definition is for a simple curve. Okay, so a curve is simple if there are no self-intersections. As an example, maybe this is a simple curve. But this is not a simple curve. This is not simple. Why? Because we have a self-intersection. Good. A curve is closed if there are no endpoints. Okay. So here we have a closed curve. Because you cannot pick an initial point and an end point because it's closed. Okay, so now a curve is positively oriented if it is a simple closed curve that is traced out in a counterclockwise direction. So let's say we have a closed curve. Now as your parameter t increases, let's say your curve traced out in this counterclockwise direction, then you have a positively oriented curve. Since we are dealing with vector quantities, so this direction is very important. Okay, so in another way, if you walk on this, let's say you walk on this curve, then the region bounded by this curve should be in your left hand side. So if this is your region, this is the region bounded by the curve, and it is in the left hand side of your hand. Okay, now here's the basic idea of the Green's theorem. Actually, Green's theorem connects a line integral over a simple closed curve to a double integral over a region bounded by the curve. So again, remember this. Green's theorem will connect the line integral over a closed curve to a double integral over the region bounded by the curve. Okay. So now we are ready to state the theorem. Let's state the theorem, Green's theorem. It's very simple, but it's very powerful theorem, Green's theorem. Let's say we have a closed bounded domain, positively oriented closed curve, and we have a region D bounded by this curve. That's your region D. And so this is your curve C of T. Okay. So let's state the theorem. Let D be a simply connected region so we have a very nice region that is bounded by positively oriented simple closed curve C. Let's say if the vector field F So we have a two-dimensional vector field F. By the way, we have a region in a plane. Basically we have a region D on the xy plane, because we have a vector field in R2. Let's say we have a vector field F equals to P of x comma y comma Q of x comma y is continuously differentiable sorry about that, I think is continuously differentiable on D, then line integral over the closed curve C of f dot ds, or sometimes we write the same integral like using the differential form, p of x comma y dx plus n of x comma y dy. So basically this line integral equals to double integral over the region D of partial, by the way this should be Q, sorry this should be Q, so partial Q over partial x minus partial P over partial y dA. This is the Green's theorem. So sometimes, if you remember in chapter 13.2, sometimes we expressed a line integral of a vector field like this, but sometimes we use this differential form notation to express the same line integral. But using this Green's theorem, we can connect a line integral over a closed curve to a double integral over the region D bounded by this closed curve. Now in this case your integrand is given by this expression. So Q is the second component of the vector field. So we have partial Q over partial x minus the partial derivative of the first component of the vector field with respect to the y variable. Okay, so next I'm going to consider a few examples from this Green's theorem.